Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 3.5 and discussing vector spaces and subspaces. In Chapter 3.5, we introduce the concept of a vector space, which is fundamental to linear algebra, and the closely related idea of a subspace. We will find familiar examples in 2-space, 3-space, calculus, and differential equations. To get started, let's look at some definitions. A vector space, denoted capital V, is a non-empty set of objects, called vectors, for which the following operations are defined. For any x, y, and z in your vector space V, and c and d any real numbers, the vector sum x plus y is still in your space. The scalar multiplication of any element in your space stays in your space. These two properties are what's called the closure properties, and these are required to show that a set satisfies the properties of a vector space. However, there are 10 properties in total that vector spaces will have. There is a zero vector in V such that any vector plus 0 stays itself, referred to as the additive identity. Or for every vector x in V, there's another vector, the opposite of x, it's negative, such that x plus negative x is 0, referred to as the additive inverse. The sum of 3 vectors in V can be reassociated, meaning you can add x plus y first and then z, or you could add y plus z and then x. Either way, the sum will be the same. This is associativity. Commutativity. A vector x plus y is the same as a vector y plus x. There are 4 scalar multiplication properties. There's a scalar multiplication identity. 1 times anything is itself. The first distributive property, saying that if you have a constant times the sum of 2 vectors, you can distribute the constant to both of the vectors. The second distributive property, that if you have the sum of 2 constant times a vector, you can distribute the vector to each of the constants. Or associativity of scalar multiplication. The product of c times some scalar version of x is the same as the scaled version cd of x. This is associativity of scalar multiplication. Now, in general, when given a set and if you're asked to see if this set satisfies a vector space, you do not have to check all 10 properties. In general, if you're asked to verify a set satisfies the requirements of being a vector space, you must only check these first 2 properties. However, I will frequently ask, because I think it's easy to do so, is there a 0 vector in your set? Because if not, then it's easy to say that a set is not going to be a vector space. Similarly, I may sometimes ask, is there an opposite of a vector, a negative of a vector? Because if not, then that would be a nice way to conclude that a set is not a vector space. Graphically, the way I think you should think of a vector space is like this. If you have some element in your space, call it X. And you have some element in your space, call it Y. Then you must be able to add these two vectors together and stay inside your same space. Or you should be able to scale any element in your space and then stay inside the same space. Let's look at some first examples. And let's consider our first vector space, referred to as R2, is the set of all ordered pairs x comma y. Typical elements in R2 look like this. And I'm going to represent sets usually in braces like this. So maybe one of the elements we could talk about would be the vector 2, 1. This is an ordered pair. It lives in R2. However, if this vector is in there, then its negative must be in there. Notice that -2, -1 is still an ordered pair. The 0 vector has to be there. And the 0 vector is an element of R2. The vector 0, 1 has to be in there. And if that vector is in there, then any multiple of it has to be in there. So if this is some vector, then 3 times that vector has to be in there. Or let's do 2 times that vector has to be in there. And if I were to say, maybe let this one be vector x and this one be vector y, then the sum of these would have to be in there, which would be 2, 3. Notice this is still an element of R2. And there is an infinite number of vectors in this space. If we want to show that the vector space R2 is really a vector space, we would have to show the following requirements. First, the addition requirement. If you take the vector 2, 1 and add it to the vector 0, 2, this new vector in general would be 2, 3. And I ask, would this be true for any of the elements that we've listed so far? If you add any of these together, will any sum stay in R2? And I'd like you to say, yes, this is still an element of R2. This will always be an element of R2. And so we can satisfy the addition requirement. The scalar multiplication property. If you take any scalar and multiply it times a vector that lives in your space, the resulting scalar product would be maybe 6, 3. Notice that this is still and will always still be an element of R2. Check. Is there the presence of a 0 vector? And the 0 vector in R2, we want to know looks like 0, 0. And this is in R2. These 3 requirements have been met, and so we can say R2 is a vector space. Now, sometimes it's really helpful to view vector spaces graphically when possible. And so maybe let's draw a little visualization of what this vector space looks like. And let's take the vectors that we use for addition, the vector 2, 1. The vector 2, 1 would point 2 in the x direction, 1 in the y direction, and it would maybe be a 2-dimensional arrow pointing to the ordered pair 2, 1. I think I want to extend my y-axis a little bit more here. And let's take the vector 0, 2 that we used. 0, 2 would be another vector. It'd be pointing 0 in the x direction and 2 in the y direction. It would be this vector. So this is vector y, this is vector x. Now, recalling from what we remember in trigonometry, if you were to add 2 vectors together, you could use the head-to-tail method, which would say, pick up vector y if you'd like, and move it to the end of vector x. So maybe it would be here. This is also vector y. Remember, a vector has length and direction, but its starting point is arbitrary. So I'm moving it to be over here, to where vector x ends. Then we could say that vector sum is going to be the vector that starts at the origin and moves to the end here. This is the vector x plus y. Notice that the vector sum x plus y will always still stay inside R2, which is this entire space. You add 2 vectors in R2, they will stay in R2. Similarly, if you took a vector x and you wanted the negative of x, well, that'd be a vector that pointed in this direction. This would be the vector negative of x. Notice that the negative x is still in R2. So for our first vector space, R2. The next vector space I'd like you to think about would be R3. R3 is the set of ordered triples. And I did recognize I said ordered pairs right there, so let's fix that. They're ordered triples. I think ordered triples only has 1 P, actually. Ordered triples. Typically, elements in R3 might look something like x, y, z, such that x, y, and z are each elements. This is your element symbol. They're members of the real numbers. To show that vector space R3 really is a vector space, you'd have to show that it satisfies the three requirements. To show that if you add two vectors in R3, they stay in R3. A nice way to do this is maybe grab two vectors. Let's grab vector 1 plus vector 2. And if these vectors are each in R3, they may look something like this. x1, y1, z1, plus another element of R3 might look like x2, y2, z2. And if you add these two vectors together, your sum is still going to be in R3. When you add these vectors together, there's no way they're going to end up living in R2. A three-dimensional vector plus a three-dimensional vector is still going to be a three-dimensional vector. It's not going to consist of four numbers all of a sudden with four elements in there. It's always going to have just three numbers. Scalar multiplication. Grab some constant k times some element in R3. If you multiply a scalar times a vector, then you distribute the scalar to each element in your vector. But this vector will still have three components. That is the requirement of being in three space, is that you have three components in your vector. And this will always still have three components. So this is still an element of R3. Is there a zero vector in R3? The zero vector in R3 will be an ordered triple, all of the values, all of the elements containing 0. That's in R3. Is there a negative of every vector? So if I said, if you were given some vector x1, y1, z1, then its negative would have to be negative x1, negative y1, negative z1. Notice that this is still an element of R3. Now again, you don't have to check all requirements each time. The ones that you are required to check would be the vector addition and the scalar multiplication. These are required. However, I like checking these two because these are easy and generally quick, Q-U-I-T, quick to verify. And if your space does not have these, then you can say that there's no way it's a vector space. And just like within R2, if you'd like to, you can think about this visually. It's a little more tricky to draw things in 3 space. But if you were drawing things in 3 space, you'd have an x-axis, a y-axis, a z-axis. And you'd like to be able to visualize that if you took any vectors in 3 space that you'd be able to add these together and you'd be able to stay in 3 space. You're not going to jump to a 4th dimension. Okay, I'd like to practice some more vector spaces with you still, some other types of vector spaces. But before I get there, I want to move on and introduce the idea of a subspace. So here we go. A subspace. We use the letter W, usually represent a subspace. A subspace, W, of another vector space V is a non-empty subset of V. It's a non-empty subset of V such that for any U and V in W and any C, any real number, the closure properties still hold. Meaning that when you add your U and V, you still stay in W. Or if you do a scalar multiplication of anything in W, it stays in W. Graphically, you'd like to visualize it like this. If you have some vector space V, then W is going to be a non-empty subset of V. So maybe W will look something like this. It's a subset. So it's contained within V. And it's not empty, so there has to be some other items in here. So here's maybe U, here's maybe V. When you add these together, U plus V needs to stay inside W. If U plus V ended up being here, then you would no longer be in W. So you need to be able to add them and stay inside this space. So it would not end out here. And similarly, any scaled vector of inside W has to be inside W. It cannot end up out here. It has to stay inside W. So consider this set W that's given. It's the set of ordered pairs where X is always greater than 0. Is W a subspace of R2? Now there's different ways you could approach answering this question, but sometimes I find it easy to give some typical elements. Some typical elements of W might be things that look like 1, 2. That's inside W. Remember, Y can be any number, but X has to be greater than or equal to 0. So 1, 2 is in there. So is 2, negative 3. That's in there, because notice that X is still positive. Y could be any number. 0, 0 is in this space. Zero, 3 is in this space. 3, negative 1 is in this space. Okay, and there's lots of things in here. I just wanted to write out a couple of them. And I'm asking, will this be a subspace of R2? Now, what you're required to show me is either this is a subspace, or show me why it's not a subspace. In which case, you need to show me that it satisfies vector addition and scalar multiplication. Again, sometimes I find it nice to also maybe show that 0 is in this space. or that for any vector u, its negative has to be in this space. There's lots of ways you can do it. So either you have to show me it's a vector space by showing it satisfies these first two requirements, or showing me maybe it doesn't satisfy some other requirements that are in there. Okay. I really like thinking of this problem graphically still. So again, we're talking about R2. So we're talking about the ordered pairs x, y that live in the plane. However, we're restricting ourselves to just things that live where x is greater than or equal to 0. So things that live on this right half plane. So let's imagine taking some vectors that live in this right half plane. Maybe the vector 1, 2. Now, the vector 1, 2, of course, is 1 over 2 up. So the vector 1, 2 would be pointing here. And maybe the vector 2, negative 3. The vector 2, negative 3 would be 2 over and 3 down. It would point to this spot. So if we're saying let this be vector x and this be vector y, if you add these vectors together, will they stay in this right half plane? And again, I'm going to use the head to tail method. Here's vector x, here's vector y. I'm going to pick up vector x and move it over here. Remember, vector x moves 1 in the x direction, 2 in the y direction. So I would move 1 more over and 2 up. So from here, move 1 in the x direction and 2 more in the y direction. That this is still the same vector x. And so the vector sum x plus y would be this green vector. Notice that this vector sum stayed in the plane. It might be kind of feeling like the vector sum is satisfied. If you add two vectors in this right half plane, will it always stay in the right half plane? So maybe I could write it like this way. If I took some vector v1 and added it to some vector v2, and let's grab two vectors that start in here. Let's just call it x1, y1, and added it to another vector, x2, y2, where x1 and x2 are both greater than or equal to 0. Then when you add these together, will this new vector, when you add them together, will x1 plus x2 still be greater than 0? That's the only requirement here, is x be greater than 0, y can be anything. If your elements x1 and x2 started individually being greater than or equal to 0, will the sum still be greater than or equal to 0? And I want to say yes. If x1 and x2 are both positive, then the sum of two positive numbers is still positive. This would still be an element of W. Check. How about the scalar multiplication? would some scaled version of a vector in this W still be in W? So maybe you could look at 2 times the vector 1, 2. This would be equal to the vector 2, 4. And that's still in W. But now I would like to ask you to be creative. Will this always be in W? What if you did -3 of vector 1, 2? Then this would now be the vector -3, -6. And this is not in W. Because remember, to be in W, we had to have that x be greater than or equal to 0. And I just found a scaled multiple that's not in W anymore. Similarly, you could have asked, is there a negative of any vector in W? So that being said, could I say, if I give you the vector 2, 3, the negative would have to be -2, -3. This would give me the 0 vector. But the problem is -2, -3 is not in W. So maybe putting all this together, we should be able to say W is not a subspace. While it does satisfy the closure of addition, taking 2 vectors in W, they will always stay in W, but it fails the scalar multiplication property, and it fails the presence of a negative vector. So W is not a subspace. Let's try another example. Consider the set W, the set of ordered pairs x, y, where y is always double what x is. Is this a subspace of R2? So is W a subspace of R2? So let's think again, what do elements of this set W look like? Now there's, again, lots of ways you can visualize this. And we don't have to do it every way, every time. But I want to give you some tools you could use. So typical elements of W. Maybe if x is 1, then y has to be always double x. So y would have to be 2. If x is 3, y would have to be 6. If x is -1, y would have to be -2. Notice that I just showed the presence of a negative vector. If x is in here, this is -x. And that's still in our space. If you took 2 vectors and added them together, would you still stay in your space? So let's say if this is y, and if you added x plus y together, then that would be 4, 8. And notice that this still satisfies that y is double x. Is there a 0 vector? I think this also satisfies. If x is 0, 2 times 0 is still 0. That's in there. And there's lots of others. So I'm just writing out a couple of typical ones. But if I really want to show this is a subspace, I want to show it in general. So let's show that this works in general. And let's show the addition property. It looks like I couldn't spell addition there. Let me try that again. ADT, ADD, ITION. So imagine some element in W. Maybe it's A, and then the Y value would have to be 2A. And let's add it to another element of W. If X were B, Y would have to be double that. Notice now that if we added these two vectors together, again, where you add vectors is you add their corresponding components. Notice, though, you could factor out a common factor from each of these y terms. And notice that the resulting sum is still of the form that y is double what x is. This would still be an element of W. For any A and B that you chose, this would always work. Let's look at the scalar multiplication. If you let k be any scalar and multiply it times an element of W, meaning that given some value for x, y is always double that. A scalar version of this vector might look like Ka 2Ka. Remember, when you scale a vector, you distribute the scalar to each element of your vector. So I distributed the k to each element. But notice, though, I could rewrite this as Ka and 2 times Ka, so that your y component is still double whatever your x component is. This is still an element of W. Is there a 0 vector in W? 0, 0. I think we already did that one. If x is 0, y is 2 times 0, which is still 0. This is an element of W. In general, I should be able to say W is a subspace of R2. Check. Again, you must always show the closure properties, the addition and scalar multiplication. These are required. The other ones that I'm checking with you, these are just nice to check, but not required. And if it failed, maybe the 0 vector, if it failed the presence of there being a negative of another vector, then that would tell you it's not a vector space. But all that's required, again, is the closure properties. Let's look at another example. Is W, the set of ordered pairs where y is equal to x plus 1, a subspace of R2? I'd like to give you a minute to look at this one on your own. So if you could maybe pause the video and verify that it satisfies the closure properties, or show that it does not satisfy one of the other properties. After you've taken a moment to think about it, unpause the video and let's see if we agree. I will see you in a moment. Okay, let's see how you did. So W. Again, I like writing out some typical elements just so we can get a handle on what elements of W look like. So maybe some typical elements of W might be if X is 0, Y is 1. Plug in 0 here, you get Y is 1. If X is 1, Y is 2. If X is 3, Y has to be 4. If X is -1, Y is 0. If X is -3, Y has to be -2. So here are what some elements of W might look like. Again, writing out some elements gives you a visualization on what this W might consist of. You may also look at it as graphically. So maybe draw a coordinate system. Y, X. And recognize that that this is an equation we know. This is a straight line with y-intercept 1, so here, and slope 1, meaning if you go over 1, you'd go up 1 more. Or if you went down 1, you'd go over 1 more. So here we're talking about the graph of a straight line. This is my best straight line I could draw. Maybe I'm going to cheat and make my dots just a little bit bigger. There, now that works. So it's a graph of a straight line with a y-intercept of 1 and a slope of 1. And we're asking, is this set W? Are these elements? Does this graph describe a subspace? Now, we could show vector addition. We could show scalar multiplication. Or we could show it fails one of the other properties. And one of the ones that I typically like to show is the 0 vector. Is there a 0 vector in this set? And the 0 vector here would be right here. Here's your 0 vector. It's the vector that contains 0, 0. Notice that 0, 0 is not in your set. Zero is not in W, since it does not go through the origin. And notice that 0, 0 does not satisfy my equation. 0 is not equal to 0 plus 1. Here I'm letting x and y both be 0 in our original equation. Let this be 0, let x be 0. It does not make an equality. So putting this together, we can say W is not a subspace. It's not a subspace. Now, I could have verified that addition does not work either. If you take the vector 0, 1 and add it to the vector 1, 2, then what we get back is the vector 1, 3. Notice that 1, 3 would not live on this line, and it does not satisfy this equation. So also does not satisfy vector addition. You also could have showed that it fails scalar multiplication. If you took the element 0, 1 and multiplied it by 3, 3 times 0, 1 would be 0, 3, which is not on the graph of this line. It does not satisfy this equation. So again, there's lots of ways you can show that a set is not a subspace or a vector space by showing that it can fail any number of properties. You don't have to show every one, you just have to show at least one that it does not satisfy. Now we've looked at 3 examples of subspaces of R2. Now, if I look back, we said, does this right half of a plane represent a subspace? And we said, no. It's a lot. It's half of your space. It's half of R2, but it did not satisfy the requirements. We looked at a line. It satisfied it. We didn't look at this one graphically, though. Let me add the graphical visualization to this. This one said, here's y, here's x. This one we recognize as a straight line with y-intercept 0 and slope 2. So if you were to go over 1, you'd have to go up 2, go over 1, you have to go up 2 more. This one was the graph of a line that went through these points. This one was a subspace. So the half plane, this example, did not satisfy the required properties of being a subspace. This first line, going through the origin actually, it was a subspace. This next one, this third line, line with slope 1, y-intercept 1, this one was not a subspace. So what I'm trying to do now is kind of put all these together and say, well, what are the subspaces of R2? Can we generalize just from those 3 examples? And to help you with that, I'm going to say there are only 3 subspaces. And one of them comes from our last 2 examples. If you think about lines, when would a line be a subspace? And we would say from our last example, well, it didn't contain a 0 vector. So if we want a line to be a subspace, it has to go through the origin. So we can say, let me just type this in. Any line through the origin will be a subspace. So maybe specifically we're thinking of things that look like y equals ax, such that a is an element of the real numbers. Anything that looks like this, any line through the origin, that'll be a subspace. Now the other 2, these are interesting ones. We can say also all of R2 itself. So when we were visualizing our vector spaces, if here is your vector space V, what if W was not completely contained inside it, but what if W was actually the same size as V? So I guess we'd be saying here W is less than or equal to V. That was technically a subspace. It's contained inside of it. And the third one is only the zero vector. So maybe if it's just this one point inside W, just the zero vector only. And in R2, that would look like 0, 0. Now, this is kind of trivially true, because if you were to take 0, 0 and add it to 0, 0, that's still 0, 0. You satisfied the closure of addition. If you multiply 0, 0 by any scalar, it's still 0, 0. It's kind of trivially true, but it is technically a subspace because it is contained inside V and satisfies the closure properties. Let's try extending this to R3. And I'll tell you now, there are actually 4 subspaces of R3. And so I'm thinking about what these 4 subspaces might look like. And I want to compare it to what we know about the subspaces of R2. One of them would be still any line through the origin. Now, Calc 3 is not a requirement for our class, but if you've taken Calc 3, then you might recognize that we're talking about the space of vectors or vector functions R of t that are equal to a, b, c times t such that a, b, c are elements of the real numbers. This is one version of what a line in 3 space might look like if you write it as a vector equation. Now, knowing this is not required, but I'm adding this just for those of you that have taken Calc 3. If you're talking about a line through the origin in 3 space, then you're talking about things that look like this. Okay. Another element or another subspace of R3 would be any plane through the origin. And notice I'm requiring that we go through the origin so that we can satisfy the presence of a zero vector. Now, of course, if we're talking about planes through the origin and just recalling what you know from Calc 3, then here we're talking about the set of things that look like ax plus by plus cz equals 0, such that a, b, and c are elements of the real numbers. This is what a plane through the origin would look like. And this is something that you should recall if you've taken Calc 3. Now, the other 2 subspaces of R3 would be all of R3 itself, or the zero vector only. Of course, in R3, the zero vector would look like an ordered triple, so 0, 0, 0. Okay, so I feel like we've done a lot of examples in R2 and R3 right now, but I want to now extend the idea of a vector space beyond that. There are actually lots of other vector spaces. Our author presents 6, 7, 8, I think 9 spaces here. He refers to them as other prominent vector spaces, ones that we typically see. So I've listed R2 and R3 so far. R2 is the space of all ordered pairs, or R3 the space of all ordered triples. But in general, we can extend this to the space Rn, n tuples. So here we would be talking about sets of vectors that didn't have 2 or 3 components in it, but Rn would be the set of vectors with n items in there. So x1, x2, dot, 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 xn, n components, such that x sub I is always an element of the real numbers. That's a terrible R. Let me try that a little better. Where xi, each of your elements is a real number. Okay. Others would be the space of all polynomials. The space of polynomials of degree less than or equal to n. The space of all matrices of size m by n. Or Ci, this is one that you're going to want to remember, is the space of all continuous functions on some interval I. And this should be a concept from calculus you remember. If you take two continuous functions and add them together, it's still a continuous function. Cni is the space of all continuous functions on an interval I that have n continuous derivatives. Or Cn, the space of all ordered n tuples of complex numbers. So complex numbers is always a vector space. If you take two complex numbers and add them together, you still have a complex number. And maybe a quick little example so we can see that. If you took the complex number 2 plus 3i and added it to -1 plus 4i, this would still be 1 plus 7i, and this is still a complex number. So complex numbers are vector spaces. And there are a couple of others out there. Now, I'm going to stop this video here, and I'm going to do a second video where I look at some of these other prominent vector spaces and some examples with them. I hope this is helpful, but I will continue this in the next video, and I'll see you then.